So we start with the action as a functional over fields. It's a 5-4 theory. The 5-4 term corresponding to the interaction between, say, Ising spins. And then we constructed this momentum shell RG where we define regions of the K integration which correspond to slow and fast fields. And with this designation, we split the Gaussian piece of the action into a slow and fast piece, and the interacting part, which comes from the 5-4 term, we haven't dealt with too much yet. We're starting to deal with it now. So again, the goal is to construct an S prime that's self-similar to that action S. S prime is the action after one RG step. And we're doing that through an integration over the fast modes, which left us with an expression like this. That has an expectation value of e to the minus s interacting over the fast fields. So this defines it as a Gaussian average over the fast fields via this formula here. And then last class, what we started doing was expanding that exponential, okay, the expectation value of that exponential using this cumulant expansion. Which means we want to calculate something like this. Right, so what's left is S prime over the slow fields. And we have sort of a first order cumulant. And then a second order piece. All squared, 0 fast. So we need to know how to take these types of expectation values, so Gaussian expectation values of, not only S, but S squared and all these higher order cumulants. So last time I wrote down Wick's theorem, so some of you have seen it and some of you haven't. I found I think the proof I do in 733 is actually kind of fun, so let's actually just go ahead and prove it. I wrote in terms of complex fields last time, which gets a little messy because you have all these real and complex components. So let me just do a proof with real fields. So the goal is to calculate these expectation values, basically. Okay, and we're going to use the Hubbard-Stratanovich transformation, which is just a generalized Gaussian integration, especially for this type of thing. And then for the higher order cumulants, we're going to use this Wick's theorem, which I mentioned last time. So I'm just going to do the general proof. I'm going to try to use the same notation as when I derived the Hubbard-Stratanovich transformation. Although I sort of forget what that was. But I use real variables x. And I think I used A and B for the Gaussian, in terms of the Gaussian integral. What I wrote down last time was M. Because I had a, what did I have? It was a Hermitian matrix, right? Okay, I'll use that. So I'll say M, but I just want to use a real. Okay, so positive eigenvalues. So I called this, I think, either A or B. A in the proof of the Hubbard-Stratanovich, which we did like a month ago. Okay, so we want to basically calculate the expectation value of several variables. So you imagine fields, fast fields occurring in S int, right? Weighted by the Gaussian kernel, if you will, or the probability distribution. I'll give this a number. I'll say n variables. So let me label with i's, x, I, n, and this is Gaussian because xi2, xi n. So I need the transpose of this vector, the matrix M. Okay, like that. And then what I'll do is, okay, so M is related to, it's going to be related somehow to, the interaction. We'll see what it is. And X will be the field vector. Okay, so we're imagining those phi's as like these real variables. Okay, so this is what we want to calculate. So in order to do this, we introduce the concept of a generating function. So to not be too formal, all that is the idea is that you have a bunch of derivatives, and when you have derivatives of an exponential, they bring fields down, right? Or they bring the argument of the exponential down. So what we need is we need to generate somehow all of these x, this product of all these x values from this exponential. Okay, so this xi1, this can be generated with a partial derivative. I'll call these things j. So I'm introducing these variables. Partial j I n. So I'm introducing all these things. They have to be set to 0 eventually. And what I have in there is x transpose mx x, and the extra term, which contains all those j's. I think so. This would have been b. What I'm calling j here would have been b if you look back in your notes on the Hubbard-Stratanovich transformation. Right, so it looks like that. And I need the normalization on the bottom. That's what a generating function is, basically. You take a derivative, it brings, you know, n of those, if you will, real variables down into the integral. Okay, so the nice thing about writing it like this is you can take Hubbard-Stratonovich transformation of everything in the square brackets. All right, it's exactly what we proved in terms of the Hubbard-Stratonovich transformation. And that'll give you a piece that, you know how to solve this integral. It's like root determinant, m in this case, and some 2 pi's. But they cancel with the piece that comes from this. We called these things I, right. In the notes, we call these things I, so it was like this. Oh, this should have been n here, not squared. So partial n. I'm going to draw the numerator. I, it's m in this case, j. Over I, m, and j set to 0. Okay, so again, back in the language of Hubbard-Stratonovich. Right, so you know what this is, and this is written in terms of this times, you know, the point of the Hubbard-Stratonovich transformation is you get 2 j's out after. So I have all these partial derivatives. Set j equal to 0. And then the only piece that's left, plus j, sorry to cram this in here, transpose m inverse j. Okay, so that's just via Hub-Strat. What does that mean? It's like it's the inverse matrix elements, right? So it's 1/2, you could write it m inverse, to be clear, ij, right, ji, jj. Okay, so again, if you look back and remember what we did, I'm just going to, I'm repeating certain things when we did Gaussian integration the first time. This thing here is related to the 2-point function, so I'm going to name it g. And you'll see why in a minute. So that's m inverse. Okay, so I'm just going to use G for that inverse matrix. Okay, so now the next step in this proof of Wick's theorem, if you will, is very simple. It's just to Taylor expand the exponential. So you're Taylor expanding an exponential, and that exponential is something you're taking derivatives of. Okay? So every term in the exponential, it's 1, and then it's whatever, 1 over 2 factorial, and then argument squared and higher. So every time you have a term in the Taylor expansion, you're bringing down j's. Okay, and you get n j's for the n by 2 order in the Taylor expansion. And only one term survives, because if the order of your expansion is less than, I guess, n by 2, then you don't have enough j's, and the derivatives will just turn every term to 0. And if you have any j's left over, so if the order is higher than n by 2, then this thing kills those terms because you're setting j to 0, right? So only one term survives in the Taylor expansion. To get n j's, you need the n by 2th. Only one Taylor coefficient survives, and that is, so I'm still writing this expectation value, so it's the n by 2, 1. Okay, so that comes from the Taylor expansion. I have a 1/2 in that exponential, and there's n by 2 of them. Let's keep these for now. ji1 partial jin. I've brought down a bunch of g's, or inverse m's, whatever you want to call it. Okay, so these, I'm going to be more careful with the indices. I'm going to put my ij's, I'm going to set as k's. Right, so there's n by 2 of those, which means there's n k's, k1, 2, blah, 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 all the way up to n minus 1 n, which gives us n j's. k1, k2, all the way up to. Okay, so that's what you wanted. You want n of those things. So that you take, oh man, I keep writing 2. So you take the nth partial and you wipe all those out, because when you set this whole thing to 0, well, it doesn't matter, but now there's no j's left to set to 0, and all the lower order terms also, you have too many derivatives basically. Does that make sense? So now you've written your expectation value basically somehow as these terms, these GIJs. Okay, so just remember what all this means, all these indices, and you'll get Wick's theorem. So you see there's only like one step in this. You write out the expectation value. You have to know to write it as a generating function, use the Hubbard-Stratanovich transformation, Taylor expand to get one coefficient, and then just remember what all the indices mean. Right, so this is sort of implicit, but the point is if I have an I derivative and a kth index on my j, they're all different variables. And I have an implicit sum when I write, that's like Einstein notation in the yellow there. So what this really means is there's a sum of terms. These k's occur in pairs. So that sum turns into a sum where you're matching pairs of the i's with pairs of the k's. So you have all these i's that come from, you have I1, I2, I3, I4, all the way up to IN minus 1, IN. Then you have k's. Again, the k's are pairing things together, so you have all possible pairings. So I could say, I could pair 2 and 3 with K1, K2. That's just some random one. I could pair, I don't know. This could be K1, K2, K. What did I miss here? Oh. K1, 2, I don't know, 3, doesn't matter, 4, K5, K6. I don't know if that makes sense intuitively, but that's what you're doing is you have pairs of Ks and you're matching them with all sorts of different pairs of I's. And that's what occurs in the sum. So from all those different pairings, you just have to ask, how many different ways do these indices get assigned to the G's? Okay. It's GI, I don't know, IN minus 1, say. K1, that's K1, K2, K3, and K4. Oh, well. I got those backwards. Whatever, G. Say 4 and N. So there's all these terms that look like that. And the question is how many? Okay, so in order to do that expectation value, you have to basically write all these terms out. So you have to know combinatorically how all those pairings occur. And there's two factors. So one is interchanging within pairs. So I could switch, say, 3 and 4, or 5 and 6 within that pair. So you have n by 2 pairs, and you have two possible configurations. Two possible configurations, n by 2 pairs. And you can also permute pairs, right? You can permute. I permuted one of those by accident. By permuting all these different pairs, it's a factor of, so it's the factorial of how many there are. So it's n by 2 factorial. And by magic, those two combinatorial factors cancel exactly these two factors here. Okay, so that's kind of the weird part about this proof, or the tricky part. So all the combinatorial, there's no prefactors. So xi1, xin, Gaussian, gi, call it 1. I labeled it with a p last time, but I'm just going to call it 1, 2, 3, 4, n minus 1, n, right? Plus, according to this combinatorial counting all other perturbations or all other pairings. That's the same as what I put on the board last time. It's just a different way of seeing it. Each pairing has to occur only once. That's the other condition. So each possible way of matching up indices in this diagram only occurs once. So that's another way of writing Wick's theorem. So it's basically this. I think that's the easiest proof. Okay, so again, just defines a generating function, do Hubbard-Stojanovich transformation, Taylor expansion, and then just think about the indices. Think about what that means, or that matrix vector, vector matrix vector multiplication. I could have called this 6-5. Or, I matched, say, 5 with 4 and 6 with n here. But I could permute that number within the pairing. So each pairing has two possibilities. So each line there.
It's because it's symmetric.
Yeah. That's because M or whatever, is a real symmetric matrix. Yeah. So it seems like, it seems like magic that these combinatorial factors cancel, but I mean, that's just, you can do this proof without that cancellation. There's other ways of looking at this. Okay, so if I have x1, x2, this is just what I would call G1, 2. It's like there's two indices and one way of pairing them. Okay, so the 2-point function, this is important. The Gaussian expectation value of the 2-point function of these real variables is just related to the, the matrix, say M, which is what G is, right? I did some examples last time when I had the complex fields. The one that you'll probably use is something like this: G1, 2, 3, 4, 1, 3, 2, 4, 2, no, already over here, 1, 4, 1, 4, 2, 3. So again, all you need to know is the 2-point function. So it's like, if you think of pairing these indices, 1, 2, 3, 4. So the first one is 1, 2, 3, 4. 1, 3, 2, 4. If you have repeated fields, you do the same thing, except some of these pairings are equivalent. Well, it's just like you have 3 times G, I would call it 1, 1. So it's like you have one index, 1, but you have 3 fields coming out of it. That's 1, And then you have 4, index 4, with one field coming out of it. And you have to think of all the different ways you pair this. So it's like, well, you know, you got to form a loop with 2 of these and pair the other one. Loop with 2 of these, pair one. Loop with 2 of these, pair one. When we do Feynman diagrams, that's basically what happens. Is you look at, it's all the sort of combinatorial pairings of these different indices. So I'd say that's the tricky part of this type of proof, is keeping track of what these indices mean. But we'll get lots of practice when we start looking more at Feynman diagrams. So I want to get back to this cumulant expansion now. Okay, so what we're going to do is use, you know, both the expectation value, so both the fact that x1, x2 is equal to, you know, g1, 2, and g is related to the argument of that exponential. We'll use that in this part of the cumulant expansion, the first order term. And then by the second order term, you see we're going to get higher order, like x1, x2, x3, x4 type terms. So let's look at this real quick. Oops, minus. Okay. Okay, so we need products of, so the sort of underlying object that we need is this thing here. It's the 2-point function. We've already calculated it. Question?
What happens with like 3-point functions where you have 3 x's?
They're 0. So you have to have an even number of fields. Exercise for your mind. Yeah, so you always need an even number of fields. Okay, so let's look at the 2-point function. How do I want to define this? So remember, it's over fast fields. So we need something like, you know, we need this g, right? So that we can just always use this g whenever we have an expectation value. So it's like the expectation value of fast fields with different momenta. I'll call it K1 and K2. I'll use minus. Do I want plus or minus? It doesn't matter. Just use plus. And they're fast, and it's a Gaussian average. So what this is what I've written up there. So it's 1 over what I called Z, probably. And then the functional integral over the fast fields. K1, K2, e to the minus S naught. Written in terms of the fast fields. Okay, so that's this part here. And remember, S naught is just something we've calculated before. That's just my notation for phi k, phi minus k. So we can basically read off what this 2-point function is, because we know it's, if you know, we use the example x1, x2 is g 1, 2. Because this is a fully Gaussian integral. So we had discrete vectors there. So we have a sum. So it's easier to see maybe if you replace try replacing this integral with the discrete sum over k. So you have a volume piece there, but otherwise you have the fields. These are like your j's, your big j's over there, and then this thing is just like the inverse matrix M or G. I mean, depending on how you want to look at it. So. So you can actually write that integral and just explicitly do it, the functional integral. I used to give that on an assignment. I'm not sure if I will. We'll say maybe. Assignment 4 is so far away that you'll forget. But intuitively, it's, again, just from this, this Wick's theorem. Let's just be careful with the k's. So if k is not equal to 1 or 2, right? Because if I have k here, then I've just kept it really general. I have two labels, k1 and k2 there. Here the integrals all factorize. And the expectation value is 0. So that's a dumb case. So you need, say, k1 equals k, but then k1 and k2 are also related. Say minus k2. And again, it's just basically 1 over, that's like m, so it's like 1 over that thing. So the 1/2 is part of the integral. So it's just, it's v over k squared plus r. That's a 2-point function of the fields and momentum. You've already calculated this. We called it Q. We had G of Q. We'd written it in terms of, so you might recognize these, 1 over beta. Remember J of Q? We'd written it like that before. Then we'd solved it in momentum space, and it was T over, T minus TC, which gives you the R, and then something like, there was that kappa. So this is from a long time ago, Q squared. So we already did this. So we're doing the same integral again. So this is your R, right? Because your R is the thing that changes sign as you go through the transition, right? And then this is just some coefficient on Q, and Q is equal to K. So there's nothing new under the sun. we're just redoing the same calculation over and over again. So the way I would write this is, I would go back to the continuum. V, I would call this G naught. Okay, let me define it properly. So that G naught is K say 1. K1 squared plus R. I've just set K is equal to K1. Delta. And these two have to be related like this. Or V G naught K1 delta K1 K2 minus. And that V is related, you know, you just replace that as I have done before with 2 pi to the D in the continuum. So G naught K1 2 pi D, and that delta function turns into K1 plus K2. So that's what we will use. So I was a little sloppy with the K1s and K2s, which is why I make you do this on an assignment. Because we can get bogged down in momentum forever if we're not careful. So go through that and make sure it makes sense. So conceptually, you see where it's coming from, very simply. But this delta function's pretty important. So I went through this pretty quick. This is worth thinking about whether that delta function makes sense to you. So now we can calculate, let's do this piece here. So remember, we're still doing an RG equation. So I can do S prime equals S naught plus the first order cumulant. I can do the second, third, fourth, whatever, later. So let's just calculate that S int naught. S interacting. And I'm going to get sick of writing things soon, so this has an integral over 4 momenta. Remember, it's K1 up to K4. So let me just say that integral K1, K2, K3. Yeah, that's just shorthand notation for that momentum integral. I think I still can't fit. Let me see if I can. So there's fast and slow fields. So I've written this many times. U by 4. There's a delta function that relates them all. And then there's 4 fields that I've written in terms of fast and slow modes, right? So it's phi 1, phi 2, phi 3, phi 4. And fast. And so slow and fast. Right? It's those things that are getting all mixed together, and we have to be careful with them. Slow for 2, fast. Oops, 2. Okay, so multiply all those out. You get terms that are products of slow and fast. And let me write those. There's going to be 5 of them. So let me write those 5 fields, or sorry, those 5 products of fields. A, B, C, D, E. Oh, damn. Okay, so we're going to look at each of these separately. So first of all, we have one that's all slow. Slow, 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 slow. But we have an integral over fast modes. So there's nothing to average here. So we don't need to use Wick's theorem or the Gaussian expectation values. This is giving us the slow fields that we then rescale as part of the RG step, right? So we'll keep track of those, but we don't have to calculate this integral yet. There's also a term that's all fast. So that's what I'm calling B. This is like your G of K, remember? It gives you an additive constant to the free energy. Like G of K. So it's just an additive constant to S. So. Drop it. We don't need it. Okay, so now we have mixes of slow and fasts that we can't avoid. So let me say 3 slow, 1, 2, 3, and 1 fast. And then there's also 3 fast and 1 slow. And 2 fast, 2 slow. So let me do 2 slow, I'll call it D, 2 fast, and then fast, 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 slow. So C and E, further to Hillary's question, have an odd number of fast fields. So when you use Wick's theorem on them, they vanish. That's C and E. C. So the only one left over is D. So that's when we need to calculate the Gaussian average over. So we found excuses to drop everything except for A, which is the slow fields, and D, which has an even number of slow and fast. Make sense? This is just the first cumulant term. We're going to have to go to second order to get non-trivial corrections to the critical exponents. Just FYI. It doesn't get easier. Okay, so what's left? So we need U over 4. There's combinatorial factors here I forgot. I forgot them. They're 1 for A and B, but C, D, and E have factors, right? So what are they? Like how many different ways do you choose 2 out of 4 or 1 out of 4? So it's 4 choose 1 or 4 choose 2. That's a combinatorial factors. So it's 4, 6, and 4. Which one's which? It's 4 here. If you get these wrong, you get the critical exponents wrong. Yeah. So that's 4, that's just, you know what I mean? I just wrote them in one order, but.
You can't remember them, you can read them off from Pascal's triangle.
Not enough time for me to learn what Pascal's triangle is. Okay, so I need 6. U over 4 times 6. I need that integral. Okay, what do I got in there? I got that delta function. This is probably a better way to write that. Then you have the expectation value of too fast, too slow. What am I going to call them? K1, K2. Is that it? I feel like I'm forgetting something. There's still the A term and the B term. We're going to drop the B term. This is only the expectation value of the D term. Yeah, I think that's right. Okay, so this is the Gaussian expectation value over the fast fields. So it's only defined, in that shell. So the slow modes, you just pull them out in front. These will turn into your renormalized fields. Oh my God. And it's easy because all you need is that thing, which I already argued was that thing right there. And now the delta function becomes important because the delta function constrains all the, I guess it's K3s and K4s here. So there's these 2 delta functions. That's why this thing's important, not to just fudge this. It's important to keep track of your momenta here. right? So this thing here, I'm getting lazy. 3 and 4, yeah, I labeled it there. So it's G naught K3, 2 pi d K3 plus K4. That's a crummy equation, but okay, so it's just a matter of keeping track of delta functions. So from the last one, K3 equals K4, or minus. K3 plus K4 equals 0. And so then that gives you a constraint here because K3 plus K4 is 0, so it means K1 equals K2. K1 equals minus K2. So I only have 2. I have to worry about this one, and I have to worry about one of those slow momenta. So let me give them different labels. K1 equals K, and K3 equals Q. So now we're going to have this notation where Q is going to be the fast fields that we're, or the fast modes that we're integrating over. That'll help us keep track of everything. Okay, so we can write this term. There's no big problem. So this expectation value, 6 over 4, 3 halves u. We have all these k's, K1, K2, K3, K4. Okay, so let me just write I'll start thinking about these limits because I'm going to do the rescaling soon. That's how I write phi k, phi minus k, remember? Then I have the I have the fast mode, which is K3, so that's K1, and then I have K3, which is the fast one, so it looks like this. And I've called that one Q. This one we can solve because I know what G naught is. It's 1 over K squared plus R. And we need that because we need R, because what I'm doing is this renormalization step where I'm relating S prime to this first order cumulant, right? So I can explicitly write that thing out and do this integral. I've done the Gaussian expectation value. What I'm doing now is the integral, this integral here, right? So let's just look at this real quick. r plus q squared. Q. Okay, so it's a d-dimensional integral. Let's write it in terms of the spherical polar momentum, spherical polar coordinates and momentum space. So here's some angular factor, surface area of the sphere. I think I defined that already. 2 pi to the d. Right now I have an integral over just the radius and the shell. And it's d, q, and in the Jacobian it's q to the d minus 1 over, right, r plus q squared. That's how you do these things. So this SD is surface area of the sphere and of unit radius. In d dimensions, to the pi and power d over 2. I wrote this somewhere in your notes. Okay, so we actually have to do this integral. So what we're going to do is expand. We'll do Taylor expansion of it. And we're going to form these like linearized RG equations. Okay, so we're just going to expand in terms of, let's see, it's going to be small r. Because we're going to move very close to the transition to calculate the critical exponents. And remember, r goes to 0. So that can be the parameter with which we do a Taylor expand. Let me call this integral something. Maybe I1. Okay, so the Taylor expansion we need is 1 over r plus q squared. Okay, easiest to do like that. So throw that into the integral. I got a d minus 1 minus 2. Can pull out that factor of the cutoff, lambda. So d minus 2 here. D minus 4 here. 1 minus 1 over b. Okay. It's looking good. So remember I wrote b as e to the delta L. So then I wrote the RG equations as these differential equations in L. L is the RG length scale. So let's use that. You're kind of like assuming b is small. Or no, not small. B is the scale factor, so you're assuming it's very close to 1. And then you can expand that exponential. It's sort of just a matter of taste, but it'll help us with these pieces here. So it's 1 minus 1 over b d minus 2 will give us this thing, d minus 2, which is like d minus 2 delta L, right? That's why we set that up. I'm going to factor out that delta L, which gives us a nice equation. I think it's this here, squared. Okay, so we're still working on the D term of the expectation value, this term here.
So it's 1 over b. So b equals 2 to the delta L. I think that's negative.
Yeah, it's possible. I can't remember how I defined it before. Was it e to the L or e to the minus L? Oh, this sign here has to be minus, doesn't it? Yeah. That's right. It's just a matter of pulling everything together. The D term pull that I1 out. We have an integral over the slow field still. Slow K. And that's the first cumulant. You know, we have the so let's derive the RG equations just with the first cumulant. So I can go on and get the second cumulant, but let's just remind ourselves how they work, right? So I have these L's, or this delta L. I have this piece here, and I have the slow fields that came from A. Now they're both Gaussian in the slow fields, right? So this piece here is renormalizing R, right? So let's see how that works. S, slow fields. We know what that is, that Gaussian piece. And what we just calculated was this piece, fast, slow, but we've integrated the expectation value. Okay, so that's what you need to put in to get the RG recursion relations, right? And you can keep improving on these things. Okay, so let's do the Gaussian piece first. So I'm just writing something I had before. That's slow fields. That's wrong. That should be slow. Right, so that's the definition of that. So last class we forgot about this first cumulant bit, and we just had this piece, and then we renormalized, right, the fields and K, and we got that thing I called Z, which was related to the scaling dimension of the fields and everything. And that gave us these really simple RG recursion relations, and then we've got nu as 1/2 and everything like that, right? So now what we're doing is we're adding pieces from this, and there's two pieces. There's the D term, which I just calculated here, 3u, which has an integral like this. Okay, that's the D. But I still have the A term, which is just the simple integral over all the modes, slow modes. And then slow. Yeah. Okay, so that's it for the first cumulant. Okay, so I have a Gaussian piece that had k squared plus r plus this thing now. And I have this term, right? So u is going to mix into the renormalization of r. Okay, that's what somebody asked me last class, is do you mix together u's and r's? So eventually what this means is in our RG flow diagram, the axes are no longer r and u. One of these axes is going to be tilted in some way, because we formally want to solve the eigen equation when we do this linearization. But let's just worry about that when it comes. Okay, so now what I have is something like this. Okay, I'm getting really sick of writing these, so I'm just going to write k here. So it's k squared plus r plus 3. I pull the half out front. 3u I1. This depends on k. Okay, so this piece from that first cumulant is now mixing in. And what we can do is basically the rescaling step now. Okay. So this step you can't do until you have the full expression. So if I left in the second cumulant, you don't do the rescaling until you have all the pieces together, right? So let's just stop. Imagine we're not looking at the second cumulant piece, and then do the last step of the RG. And just see what we get. So rescaling k and the fields. And we know the scaling dimension of those things. Okay, you want me to write them? Small random here. K prime is equal to, it's B times K. And then the field prime in momentum space is B D minus D plus 2 minus eta over 2. And I'm rescaling the slow modes. Okay, so I'll do it like that. Same thing we did last time. That's the first term, rescaled. And then the second term, which is the u over 4. B to the minus 4d from this integral. Still the delta function. But now it's rescaled. And it picks up a b to the d. Okay, now I have the 4 fields. So this thing times 4. So it's 2d plus 2 minus eta. And then the 4 fields are now primed. Okay, let's just set that eta to 0. You need eta to be 0 for all these dimensions to work out again. But just remember that it's there. It's there in the scaling dimension. Someday it'll matter. You say why it's called the anomalous dimension? Because it has to do with the scaling dimensions. Okay. Okay, so R prime, right, which is this piece here. Where's R? Oh yeah, R is there. It's going to be 3u I1 b squared. And u prime is simple b4 minus d. And they're coupled because they're a set of equations because u occurs in both. These are literally the RG recursion equations. And these are the things you want to analyze in order to get the critical exponents. I won't write S prime, but if you're write it out and see that it's self-similar, right? Which is necessary so that we can iterate this to infinity. Let me just analyze, let me set up some analysis for these recursion. So this is what we wanted, right? All that work took like a whole class. is to get these equations. Let's write them in differential form. Again, using b is e to the delta L. And again, we always assume that b is very close to 1. Delta L is very small. So we're expanding this out. That's going to give us these linear equations in delta L. And if you wanted to, you could remember what that integral is. We're going to erase it soon, so let's start writing it. And pretty much everything's in here. Right, because it had delta L in it here. Okay, so don't forget that. This is an approximation, but we're assuming b is close to 1. Did I do this right? Yeah, so now I have r prime minus r over delta L, right? Which is like the derivative in this RG language. Same thing, and like I say, this is, what do I call this? dr over dl. So that's a differential equation. And u, use simpler u prime up there. So and so u minus u over delta L, right? So that gives me du d. I call it, when I do this, it's L equals delta L. Oh no, that's right. So then this is just what? 4 minus d times u.
Is that R minus R1 or R1?
Should be r prime minus r, I would think. Okay, so now our set of differential equations, which remember we iterate to get to the fixed point. Looks like this. Okay, so let's analyze those next class. So I think it's interesting and sort of rare that you can essentially do an exact calculation. So we have all these tools. You know, we had to use momentum space. We had to know how to handle, you know, momentum space integrals. We need the Wick's theorem. We need the cumulant expansion. We know how to do Gaussian integration in momentum space. And then we had the framework of the RG procedure, which we kind of motivated in real space, right, with all this momentum shell rescaling and so on. And this is what it leads to. This is the point of the whole thing. Is you have these two differential equations for the two parameters. Remember, one's, you know, related to the coefficient of phi squared, and this is the phi 4 term. And this is how they are modified under one RG step up to the first order in the cumulant expansion. So we can go further later. But let's analyze these next time and see what kind of fixed point structure they give us. And we'll draw, you know, all the RG flows, look for relevant and irrelevant variables, see how, you know, this dimension matters somehow here, right? So let's see how this analysis works out. And then after we've done that analysis, we'll start looking at the second order cumulant terms. And that's what we need to get something non-trivial. And to do that, we define sort of a perturbative expansion in the distance away from 4 dimensions. It's called the epsilon expansion. Okay? So we'll start into that probably on Friday. So I'll see you guys then.